Okay, I'm going to record lecture 12. And when we study this neural network, often we use the neural network for the purpose of classification or the so-called pattern recognition. So our training data consists of input X and output Y, which is the class label. As I mentioned, for ImageNet dataset, there are 1,000 categories and 1 million images. So for each image X, we have class label telling us which category it comes from. For example, car or dog or cat or tree or whatever. And last time we studied the basic language of the neural network, the mathematical language of the neural network, which consists of two parts. One is that at each layer, HL, it is computed as a element-wise or coordinate-wise ratification for S of L. So S of L is a vector of the same dimension as H of L. And in this multi-layer perceptron, I only plot H of L, which is the activities of the neurons or the nodes after this element-wise ratification, for example, sigmoid or ReLU. And I didn't plot S of L, which consists of those activities before ratification. And this vector S of L is computed from the layer below H of L minus 1 by a matrix WL, and then plus BL, which is the bias vector or the vector of intercepts. Okay, so this is a linear structure. Only the linear structure contains the learnable parameters WL and B of L. Okay, so this is a basic language, mathematical language of neural network. So we have multiple vectors, and the vectors can be transformed by the matrix. And for each training example, we have different values for those H. But all the training examples, they share the same WL and BL as parameters for L from 1 to capital L. And those parameters are to be learned from all the training examples. And last time we studied chain rule backpropagation, where the forward path is from X to H1 until HL minus 1 HL until Y hat. And then along this backbone, so we also have the input, right, from W1, B1, W2, B2, W small l, B small l, and so on. And then for the backpropagation, so we treat this top layer, H capital L, we write this as our S. And for this score S, so we compute the derivative for the loss function for this particular training example with respect to this top layer, S or H capital L. And this is in the form of negative error. And then we backpropagate based on formula 1, which enable us to go back along the backbone, and formula 2, as we derived in the last lecture, so that we can compute the derivative of the loss for this particular example with respect to the parameter WL and BL. Okay, so that's a chain rule backpropagation. And last time we showed that for linear regression and logistic regression, the derivative is always in the form of negative E. So today we shall start from a in-depth treatment of multi-class classification. So that is our output is a class label. For example, 1,000 categories in the case of ImageNet. But for digit, handwritten digit, there are 10 categories, right, from 0 to 9 in the so-called MNIST data set. Okay, and we want to study this classification problem very carefully. The reason, there are two reasons. First, the neural network was invented mainly for the purpose of classification. And a lot of problems, pattern recognition problems, are actually a classification problem. Okay, so that's a first reason. And another reason that is also related is that in natural language processing, when we try to predict a word, this is also treated as a classification problem. Suppose we have, for example, 10,000 words in our dictionary, and then it is like we have 10,000 categories. And when we try to predict a word, either a word within a sentence or the next word, when we do this produce or generate the words one by one, and then for each word, it's like the prediction is like doing a classification problem, right? And then when we train the language model, then our loss function is also the loss function for classification. So therefore, this multi-category classification or multinomial logistic regression is very, very important for deep learning, because a lot of times our output is either or most often a category, for example, a word. Sometimes, of course, it can also be a continuous vector. In that case, we just use the least square. But for this multi-category classification, where Y is a class label, this is very common, and also the underlying treatment is more involved than regression. In regression, even if our output is a vector, continuous vector, we can still use Euclidean distance, right? But for classification, we need a more careful treatment. So that's what we want to study next. And later, when we study language model, for example, the recurrent neural network or transformer model based on self-attention. So the output will be the word, which is also considered as a category. And they share essentially the same loss function. Okay, so that we can use this classification loss to train the neural network, the network parameters. Okay, so now for classification, let's look at this Y. So Y is for each input X, for example, image, Y is a class label telling us whether it's a car or a cat and so on. So suppose we have capital C, which is 1,000 categories. We can either write Y as the label of that particular category, or equivalently, we can write this as a one hot vector. For example, if we observe Y to be the category small c, then for this one hot vector, which has capital C elements, only the small c's element is 1. All the rest of the elements are 0. So this is a one hot vector, which is also a way to label a class, right? So you can also treat this Y, this one hot vector, as our Y as a class label. And the way we predict the class label is based on the so-called logic scores, which is our top layer vector in this multi-layer perceptron. And the logic scores is the vector also a C-dimensional vector for continuous scores. They're unbounded, they're continuous. So therefore, for prediction, we only need to see which score or which category has a maximum score. And if this category has a maximum score, we then classify Y to be that particular category. So this is like taking the argmax, right? We look at which element achieve the maximum score. But for a probabilistic treatment, we rather want to first use this S to compute a probability. So this is not just taking the argmax. So we do this like a softmax. So softmax means that we want to translate this score S. So this vector S, which consists of all the logit scores, into a vector of probabilities, so that those probabilities sum to 1. Okay. So the logit scores are unbounded continuous values, but the probabilities are all between 0 and 1, and they sum to 1. So we treat this P probability as a prediction for this Y. And again, I want to mention that this is also how we predict a word. For example, when we want to fill in a missing word or masked word, or when we want to generate the next word when we speak, then we can first use neural network to compute this the vector of logit scores. And then we use softmax to translate this into probabilities. And then either we generate a word that get the maximum probability, or we actually sample from this probability so that the word are generated according to those probabilities. We can also do that. So therefore, we want to study this softmax transformation. So it is based on this transformation. So we write P sub C. So this is, we exponentiate S of C, and then we divide all those exponentials by the summation of those exponentials, sum over C from 1 to capital C, e to the power IC. So here I use C prime just to avoid confusion, because we have reserved C for this particular category, and this is just a summation. And we can also write this as e to the power S sub C divided by Z. So Z is often used as a notation for normalizing constant, which is a summation, okay, of the exponential, so that now the summation of P of C equals 1 for C from 1 to capital C. Okay, so this, we first exponentiate to make it non-negative, and then we divide this by the sum so that those probabilities sum to 1. So we really got a probability distribution. So you can think of this P as a prediction of this one hot Y. It's like we smear this 100% into all those categories. Okay, and so this is a softmax computation, which is commonly used in pattern recognition, classification, and also, as I mentioned, language model. So we use our neural network to compute this S, top layer S, okay, as a vector of logit scores for different words. And then we do this softmax normalization or transformation to get a probability. So if we have, say, 10,000 words, then we have 10,000 probabilities. And then we can generate a word either as a word with the maximum probability, or we sample the words according to this softmax probability. Okay, I keep mentioning this language model because later we are going to study the language model, such as recurrent neural network and transformer. So I just want to emphasize this connection, because later I'm not going to repeat this treatment again. Okay, so now let's move on to study the training for the model. So suppose we have one training example, a single training example, where the input is X and the output is Y. Okay, so this is for a single training example. And then we get the so-called likelihood. The likelihood is the probability for the observed category. Okay, so we can although we can write this in terms of English, so suppose the category is C or K, for example, K, and then we should return P sub K, right? And how do you write in this mathematical form? You can write this as the product for C, small c from 1 to capital C, and P sub C to the power Y sub C. And we know that this Y sub C is element, right, of this one hot vector. So only one for a single, there's only one C, small c, so that Y sub C equals 1. And for the other C's, Y sub C are equal to 0. So therefore, suppose the observed category is K, and only Y sub K equals 1, right? And all the other Y sub C for C not equal to K, they are all 0. So therefore, this product gives us a P sub K. Because only when C equal to K, we have P sub K to the Y sub K, which is 1. Okay. For a different C, we have P sub C to the power Y sub C, where Y sub C equal to 0. So P sub C to the power 0 equals 1. It doesn't fit into this one. So therefore, this likelihood essentially gives us the probability for this observed category. And we want to maximize this likelihood so that under the model parameters or under the trained neural network, this probability should be very high. So that's the basic idea for maximum likelihood. And this is a product is not very easy to deal with. So therefore, we perform a log transformation. Log is a monotone transformation. So therefore, if you maximize the log likelihood, it's the same as maximizing the likelihood itself. And then if we take log, this product becomes the summation, C from 1 to capital C, and the Y sub C log P sub C. Okay. And remember that we define P sub C by softmax. So in the softmax, P sub C is E to the power I sub C divided by Z, where Z is a summation. So if you take log, then that will be S sub C minus log Z, right? So that's what we will have in the next page. Okay, so therefore you see we get this Y sub C and S sub C minus log Z. Okay, so this is taking log of the softmax probability. And then we can write this as summation Y sub C, S sub C minus log Z. We can move this log Z out because summation of YC equals 1, because only one of Y sub C equals 1. All the others are 0. So therefore, the summation also equals 1. So we get log Z. Okay. So this is our log likelihood for a single observation. And then we want to maximize this log likelihood, which means we want to minimize the negative of log likelihood. So we can define the loss function for a single observation as a negative log likelihood, which is negative summation over all the categories, Y sub C, I sub C minus log Z. So this is the loss function that we use for classification. And this is also the loss function that we use for language model when we try to generate, for example, the next word. Okay, in the translation situation, for example, the input is English, output is Spanish. You want to predict the probabilities of the Spanish word, and then this is our loss function, so that Y of C, the Y is one hot vector for the observed word, and then you plug in this Y, and then you get this loss function. Okay, sometimes people also call this as cross entropy loss. That is for classification. We use maximum likelihood, and the negative log likelihood is the so-called cross entropy loss, which is commonly used for classification and language generation. Okay, so now we, as we claimed that we compute the probability according to the top layer S. this is a vector of logic score. So if we have, say, 1,000 categories, this S is a 1,000 dimensional vector of continuous logic scores. And then we want to compute this. So this derivative or gradient can be written as the derivative for this loss with respect to each of sk, k from 1 to capital C. Okay, so here we use k because we already use summations over C, right, just to avoid confusion. Okay, so now let's look at the derivative with respect to S sub k, that is the logic score for the case category or case word. And if you take derivative, this will be y. Actually, we have negative sign here, negative sign in front of it. And then with respect to sk, right? This is sum over C. That's why I use notation k. And then for the derivative with respect to sk, we get y sub k. And then minus. Now we take derivative for log z with respect to sk. And this equal to what? So let's do the calculation here. So the derivative of log z will be 1 over z, and then the derivative of z over partial sk, right? And then this is z, and then this is, because z is the summation of e of sc. Again, you take derivative only for the case element, right? You get the derivative, which is e to the power s sub k. So this is exactly p sub k. That's softmax probability. Okay, so therefore, this you get pk here. Actually, you also have negative sign here in front. So therefore, it is negative for this whole vector. This is vector of y, and this is vector of p. So if you have 1,000 categories, this is one hot vector of 1,000 dimension, and this is a probability vector that consists of probabilities of all these 1,000 categories. So this E is also a vector, 1,000 dimensional vector. And for the words, if you have 10,000 words, this is 10,000 dimensional, and this P also 10,000 dimensional, and this E is also 10,000 dimensional. But in any case, now you see that we have neural network. The neural network, after some computations, finally provide this S, the vector S, right? From the vector S, we get the softmax probability. And then when we compute the derivative of this loss function for this particular training example with respect to the top layer, S, then we get this negative E. So this, again, is consistent with what we got before for binary logistic regression, and also for the other like a linear regression, which is also in the form of negative E. And then we can go through this backpropagation as we studied in the previous lecture, right? To do error backpropagation to get the derivative for the loss function with respect to all the parameters, so that we can update the parameter. Again, here we are computing the derivative of the loss function for a single example. And in training, you should average over all the training examples for gradient update. And this type of log z is ubiquitous in physics. So z is called the partition function in physics. And the derivative for log z is often in the form of a probability or expectation. This is also extremely common in physics. You may wondering what's the relationship between this softmax multi-category logistic regression or multinomial logistic regression with a binary logistic regression. In binary logistic regression, we can actually write y to be 1 or 0, right? So for example, we have two categories, positive or negative, and then we can use one hot. The one hot vector is like 1 or 0 or 0 or 1. And then we can also write the score. Because we only have two categories, so we can simply set the score for negative category to be 0. And then we continue to use S with a little bit abuse of notation to denote the score for the partial. So here S is a scalar, and this S is actually two-dimensional vector. I'm abusing the notation a little bit. But in any case, if you look at the vector for probability, so we use P to denote the two-dimensional vector of the probabilities. But I continue to abuse notation. I use this P to denote the probability of positive or probability of 1. So this will be E of S divided by, according to the softmax, E of 0 and the E of S. And that's exact, E of 0 is 1. So therefore, this is exactly sigmoid transformation, right? And 1 minus P will be E to the power 0, which is 1 divided by 1 plus E S. Okay, so this is what we have for two category situation or binary situation. In the binary, we can also specify say S positive or S negative. But the point is that there's a redundancy in the sense that in this softmax definition, so if you add a constant to all the logit scores, if you add such a constant to all the logit scores, then you do not change the probability, because if you add a constant C, add a constant A, for example, and add constant A, so E to the power A will get cancelled. Okay, so there's a inherent redundancy in all the scores. And to avoid redundancy, you may set the score for the last category to be 0, just like what we did for binary. But if you have 1,000 categories, this is not really necessary. We don't bother with it if you have 1,000 categories or 10 categories. Only when we have 2 categories in the binary logistic situation, we set the score for negative category to be 0, so that we can work with scalar S and scalar P. So that's the connection. Okay, but for multinomial situation, for 1,000 categories or like 10,000 words, this type of things, we don't need to bother with setting the score for one category to be 0. We just use continuous values. Okay, here I just give you the connection, and the point is that for whatever neural network, however complex it is, okay, eventually you want to predict a top layer S. So if you have 1,000 categories, your vector S will be a 1,000 dimensional vector of logit scores. Okay, and if you do this, if you want to generate a word, if you have 10,000 words, then this S is a 10,000 dimensional vector. Okay, so that is for whatever neural network. So here we use multi-layer perceptron, but it can be more complex. But eventually, whenever you want to generate a word, you need to finally compute the 10,000 dimensional vector of logit scores. And then you use the softmax transformation here to transform it into a 10,000 dimensional vector of probabilities. And then you generate the word. So that's the idea. And then the loss function is always defined. The loss function is always defined as in this way. Okay, and here you get this log likelihood, and the loss function is the native log likelihood. Sometimes, as I mentioned, it is called cross entropy loss. And then you can compute the derivative with respect to this, for example, in the language model, this will be 10,000 dimensional logit scores. And then it is always in the form of negative E, which is a 10,000 dimensional one hot vector minus 10,000 dimensional this probability vector. So in the language model, for each sentence and for each word in the sentence, you have such a derivative, and you backpropagate this derivative back to all the model parameters. So this is for each single training example. Okay. So this part, actually, I ask you to reproduce this part in the homework, and for this multi-category classification. And also, after you calculate the top layer loss, so that the derivative, you get negative E, right? And then you use this formula 1, to go back on along the backbone. And then you use this formula 2 to compute the derivative with respect to the parameters. Okay, so that's the, we did this in the previous lecture. So for the, I think for the second homework problem, you need to do both the top layer and then the starting point of the backpropagation, and also the recursive formula for the backpropagation. So that's the second problem. The first problem actually is based on lecture 10, which is about this nonlinear approximation caused by this nonlinear rectification, for example, sigmoid or ReLU. So sigmoid in this nonlinear transformation give you piecewise constant function, and ReLU give you piecewise linear function. Okay. So I think this part is very, very important, and I hope you will remember it when we study language model. Okay, so now I think we can move on to study the training for the neural network after we know how to compute the derivative. So we train the neural network based on the so-called stochastic gradient descent (SGD) algorithm. So suppose we have a lot of examples. We cannot read all the training examples all at once into the computer. That will be too much. And in fact, nowadays, when people train big language model, they actually collect a huge collection of documents, books, or text, or web pages that you can find. So that's really big data. And certainly you cannot fit all the data in your computer to compute the gradient by averaging over all the training examples. Rather, you want to randomly divide the training examples into mini batches. Say you have this, each mini batch, you have some examples. So this M should be chosen to be just the maximum number of examples you can load in to your computer, for example. M may be 100, and then you randomly divide the training examples into big N for the so-called mini batches. Each mini batch you have M examples. Okay, and then you fix those mini batches after this randomly dividing them. And then you can go over those mini batches one by one. So each time you read in one mini batch, and then you update your model parameters. And then you go to next batch and do another update of your model parameters until you finish all the mini batches. So for this big like a text data, usually you only need to go over once. So this is called one epoch. But for other data, not as big but still very big, you may go over like 100 or a few hundreds for epoch. So one epoch means that you go through all those mini batches in your data set. So here I use T to denote time. So T is 1 to N, right? This is one epoch. And then in the next epoch, you go back here again and update the parameter. And then you go over all the mini batches. That's a second epoch, and then keep going. So that's the training procedure. And as I said, our parameters, model parameters, include all the weight matrix and the bias vector at all the layers. So this is for multi-layer perceptron. And then we train our model at each time step. We look at the mini batch. So we average the derivative of the loss function for each training example with respect to theta. Okay, and evaluate it at theta t. We average this over this mini batch. So that is for this current mini batch, we sum over all the examples in this mini batch. And for each training example, we have a loss function. Okay, and this loss function, we use the chain rule backpropagation to compute the derivative of this loss function with respect to theta, including all the parameters, and evaluated at current theta. So for big language model, for example, you may have hundreds of billions of parameters. So theta consists of hundreds of billions of parameters, and you have a huge number of documents or text. So you have again hundreds of billions of words in your whole training data set. Okay, and then you do this update. Okay, so for each t, it is about a mini batch. Okay, you compute the average of the derivative, and then you update theta by going along the direction of the so-called gradient, which consists of the derivative with respect to all the parameters. And this eta t is the step size, sometimes also called the learning rate. In the traditional stochastic gradient descent algorithm, the theoretical learning rate is something like 1 over t. But in modern optimizer, they have a more sophisticated schedule of the learning rate. So supposedly, originally your learning rate should be big enough, so you learn very fast. But as you get closer and closer to the local minimum, you should reduce your learning rate to allow your algorithm to converge. Yeah, so that's a basic idea for training the model. And so here, the point is that these parameters, okay, they are shared by all the training examples. And for each training examples, we have this H, right, HFL. So those latent hidden variables, but they all share the same WL and BL. And we compute the derivative for the loss computed for each training example with respect to this theta, and then we average over all the training example in this mini batch to make one update. And then next time you go to another mini batch to make another update and keep going. Okay, so this is how you train the neural network, including the language model. So in each mini batch, you have many sentences, right? And in each sentence, you have many words. And for each word, you can compute this classification loss and then backpropagate. So that's the basic idea. So now I think talking about gradient descent, I need to talk a little bit more about gradient. What's the idea of gradient? So here I use this generic notation X. Not this X is not the training example anymore. And in fact, you should compare this X to theta. But here instead of theta, I just use a generic X when we talk about the function. So X may be d-dimensional. Again, you can compare this X to this theta when we talk about the gradient. And suppose we perturb this X locally by a infinitesimal small delta X, also d-dimensional. And we perturb each element xk by delta xk. And suppose we have function f, which is a function of all those x1 to xd. So we can write this f of x, x is a d-dimensional vector, and then we can also write this f as a function of d arguments. Okay, so now we look at the Taylor expansion. If we perturb this x by delta x, and then we have f of x plus delta x, right? So we want to know how does that change. So in the one-dimensional situation, we know that there's a one-dimensional Taylor expansion, and the derivative is just a slope, right? So that's very easy to get. But we want to generalize this one-dimensional situation, or one-dimensional Taylor expansion, to this multivariate d-dimensional Taylor expansion. So that is, we can again write this f as x1 plus delta x1 and xk plus delta xk, and so on. So this first order Taylor expansion is like you have this one, f of x, this is f of x, x1 to xt. And then according to this first order Taylor expansion, we compute the derivative of f with respect to x1 evaluated at the current x1, current x, evaluated at the current x times delta x1, and then plus partial f over partial xk, evaluated at the current x, and then times delta xk, and so on. Okay, so now in vector notation, actually I put the dot here, meaning that this is approximation. But for the rest, we shouldn't put the dot here. Okay, the rest will be just equal sign. Okay, so we have this f of x, and then you can see that this is just the first term, right? For the second summation, this is in the form of a inner product. So we can write this as an inner product between two vectors. One is a vector of partial f over partial xk, and the other is a vector of delta xk. And this, we define this to be our derivative, multivariate version of derivative or gradient, and times delta x, okay? And this equals f of x plus this inner product can be written as the norm, the L2 norm of the Euclidean length for the gradient, this vector times the length of this vector, delta x, times cosine theta. Cosine theta is angle between the two vectors. And clearly, this value is maximized when theta equal to 0. So that is when delta x is along the direction of the gradient. This becomes maximized. So that is if you make the change, if you, suppose we fix delta x, we fix the length of delta x, we fix the same length, okay? So for delta x, for certain fixed length, when delta x is along the direction of the gradient, you see the biggest increase. And if theta equals pi, then it's in the other direction, you see the biggest decrease. For gradient descent, you actually go along the opposite direction, right, for the gradient, for the gradient descent. For the gradient ascent, you go along the gradient direction, okay? So that's why we call this I prime x, this gradient, why we call it as a gradient. It is the steepest direction, the direction of the steepest change. So when you climb a hill, or you go down, you climb a hill, or you go down a valley. So here, this f of x is like surface or landscape. So you go uphill or you go down a valley, either like a gradient ascent when you climb a hill, or gradient descent when you go down a valley. So the steepest direction is a gradient direction. So gradient descent always allow you to go the steepest direction. And again here, the reason that this I prime x is a steepest direction is that for any delta x of fixed length, this inner product is maximized when delta x is proportional to this gradient or along the same direction as the gradient. Okay, so that's a basic idea of a gradient descent or gradient ascent, depending on whether you are minimizing something or you are maximizing something. Okay, so actually you can derive this formula by considering a univariate function. Let's call this g of t, which is f of x plus t times u. So u is a unit vector. Its length equals 1. So it's like an axis or a direction. And the t, so we let t times u to be delta x. Okay, delta x. So u is a direction of delta x, and the t is like the magnitude of delta x. And t is a univariate value. Okay, univariate. So it's just a real number. So this way, we are probing, or we are viewing this function f of x along the direction u, so that this become a one-dimensional function. So for example, in one direction, one u, we see a function like this form, highly curved. In another direction, for another u, we may see a function like this. Okay. And why is that? Actually, I can give you an example. For example, this is like a valley. So this is the direction, the flight direction, like this direction. And this direction is a more curved direction. So this is like a valley, right? This is the bottom of the valley. And so this direction is the first u. If you look at this direction, like inside the page, we see this shape, right? And in this direction, along this page, we see this shape. Okay, so that is you can change your u, and then you are going to see different shape. And but in any case, so this become a one-dimensional function, univariate function. And we know that for a univariate function, if it is smooth enough, we can always have second order Taylor expansion, which is g0 and plus, so we expand at 0 plus g prime 0 times t plus 1/2 of g double prime, the second derivative at 0, t squared. So the first derivative is a slope, and the second derivative is the curvature. For example, here we see a negative slope. Here we see a positive slope, and here we see a very big curvature. Okay. And for this one, we see negative slope, positive slope, and we also see a curvature. So this is second order Taylor expansion. And by the chain rule calculation, we can actually see that this is f of x. So when t equal to 0, you plug in 0, you get f of x, right? And then g prime t can be written or can be derived as the inner product for the gradient times delta x. Okay. And then the second order term can be actually derived as 1/2. So this is delta x. So here this is not squared, this is delta x transpose. And then the second derivative for x times delta x. The second derivative is actually a matrix, d by d matrix. Again, this is transpose. So delta x transpose, second derivative, delta x. So this f prime x is a d by d matrix. So the ij's element will be the second order derivative of x with respect to xi and xj. Okay, so that sometimes people call this as a Hessian matrix, and people call this gradient as a score. And for this Hessian matrix, we see that the second derivative, this second order term, is in the form of so-called quadratic form. So you have delta x transpose, a Hessian matrix, which is actually symmetric, and delta x. So this quadratic form, if you change the basis or you view it from a different viewpoint, then you can diagonalize this so-called Hessian matrix into a diagonal matrix, and the diagonal elements are the so-called eigenvalues. Okay, and the new basis that you view this quadratic form is actually consists of those eigenvectors. So this is actually a very natural point to study these eigenvalues and eigenvectors. A little bit different from a undergraduate linear algebra textbook. So this, I would say, this is a perhaps the most natural way of encountering this eigen analysis. So you get eigen decomposition to treat this quadratic form, and it has a very direct geometric meaning. So if a corresponding eigenvector is very, very small, okay, then that means along this along the corresponding eigenvalue direction, the curvature is very small. If the corresponding eigenvalue is very big, then along the corresponding eigenvector direction, the curvature is very big. So it has a very clear geometric meaning. But in the high dimensional situation, it is very common that you have one very big eigenvalue. The biggest eigenvalue is very big in this situation, and the smallest eigenvalue is very small, like this. And sometimes you may even have negative eigenvalues. In that case, you have saddle point. But I think at this point, we don't need to really get into the eigenanalysis here. I just want you to be aware for eigenanalysis for this quadratic form with this symmetric matrix. As I mentioned, I think if I teach eigenanalysis, I will teach it beginning of this quadratic form and with this also very clear geometric meaning in the context of second order Taylor expansion. But I think here, understanding this picture is good enough. So along one direction, it is highly curved. Along another direction, it is very flat. So that's a very common type of situation. It's like a Grand Canyon, right? So you along this direction is flat, along this direction is very steep. Okay, so this is how we understand the gradient and also Hessian or the idea of curvature. Okay, so now we can move on to study gradient descent on the next page. Oops, I think I should be able to go to the next page. Yes. Okay. So in fact, I would like to give you a very concrete example. So suppose you have f of x, which is x1, x2, two-dimensional, and x1 squared divided by a squared plus x2 squared. Okay. So therefore, if you plot the so-called contour, the contour plot is like each contour consists of the points x1, x2, those points that give you the same value of f. So the minimum here is here, right? The origin is a minimum. So again, this is like and here the height become bigger and still bigger and still bigger. Again, it's like a valley. And suppose you start from this 1, 1, this point. Okay, and then so for this, if a is for example 10, let's just make up a number. If a equals 10, and then you have this type of shape. Okay, and then if you look at the derivative, it's a 2 because this square, right? You have 2 x1 over a squared and x2. So that's the gradient. And now if a equals 10, this will be a squared is 100. So you have 1 over 100 and 1. So that is along this x1 direction, it is very small. But along this x2 direction, it's very big. It's like this direction. It is actually perpendicular to this contour here. Okay. And then if you do gradient descent, you are going to move on this direction. So you may move here to get the 0.9, 0.9. I just make up the number. Okay, it may not be that accurate. And then if you compute the derivative, it's 2 times, again, this will be x1 plug in x1 0.9 divided by 100, and x2 is negative 0.9. So you go this direction. You go this direction. So that is now you want to go up, but you still have a direction. So when you do gradient descent, you still need to go this a little bit. So therefore, if you do gradient descent, you will get this zigzag path. Okay, zigzag path until you get 0. So that's the situation. So now we, if we just use this common gradient descent method, you see we waste a lot of time doing this zigzag, right? But imagine that if you drop a heavy ball, it will actually accumulate the speed along this direction. Okay, so rather we want to involve this overall speed, or we want to accumulate the speed. So that's the idea of momentum. So we want to accumulate the momentum so that we figure out this direction is a very flat direction. And this direction is very curved so that the ball is going back and forth. Okay, so we don't want to waste too much time going back and forth. Rather, we want to accumulate the direction along this flat direction so that our trajectory will be smoother. We keep accumulating the speed or the velocity along this direction. And the velocity in this direction, because it's a positive or negative, keep going back and forth, it will cancel. Okay, and this way we accumulate the momentum so that we can go to this minimum faster. Okay, so this is idea for momentum. And another issue we want to take care is that if you look at the magnitude along this first direction is always very small. Okay, by by 100-fold, right? So this is too small, and rather you want to update it. If the derivative is too small along a certain coordinate, you want to make bigger update. So you want to do this adaptive update. So this is another point. So you try to update the components according to their overall magnitude of the derivative. If the magnitude of the derivative is too small, you want to use a bigger learning rate, adaptive learning rate to update it, so you can update more. So this also make you go to this origin, which is a minimum faster. Okay. So the item optimizer actually combine these two ideas, the adaptive learning rate and the momentum. So item, I think it stands for adaptive and momentum. I guess that's how, so nowadays people only remember item, I guess. This is a very commonly used optimizer, which is a improved implementation for stochastic gradient descent. Okay. So recall that for each mini batch, so this should be I from 1 to m, the typo. So this is m. For each mini batch of m examples, for each training example, we can compute this loss function. And we compute the derivative of the loss function with respect to the shared parameter theta, evaluated at the current value of theta t. And then we average over all the training examples in this mini batch. So we call this as our GT. Then stochastic gradient descent is to update theta by going along the direction opposite of the gradient direction. So minus e to t and the GT. So GT is a vector for all those derivatives and evaluated at theta t. So this is SGD, but as we mentioned, SGD suffer from this like a zigzag type of oscillation. And so rather we want to accumulate the velocity so that we see this direction. So we almost figure out the curvature information. We figure out along this direction, the curvature is very small. And along this direction, the curvature is too big. So you see this oscillating. And by accumulating the velocity, you accumulating the momentum along this direction. And the momentum along this direction got canceled. So that's the idea. We accumulate this GT, we sum over this GT, and we use this formula, iterative formula, to sum over GT. As I will show you later, this enables us to compute a weighted sum for GT, where we put bigger weights to the more recent GT. It's like a windowed or a recent memory of the GT. So this VT, we use this formula. So this gamma is a number that is close to 1, for example, 0.9. And gamma times VT minus 1 and plus 1 minus gamma GT. GT is computed here, it's a gradient. Okay. And we use this formula to accumulate GT. And also we have this big GT is a beta also a number close to 1, for example, 0.9, this gt equal to big GT minus 1 plus 1 minus beta GT squared. So when we do this operation, squared or division, or this division here, it's always done element-wise. Okay, so suppose we have 1 million parameters. We do this for each of the 1 million parameters. So it's element-wise. We compute the square for each element, and we sum them also for each element. And so this Vt is a momentum. It accumulates GT, the recent GT. And this big GT is actually accumulating the GT squared. When we square it, we don't care about the sign, right? We only care about the magnitude. So basically, we are accumulating the magnitude, okay? And then we normalize. So we make some adjustment. We divide this Vt by 1 minus gamma, and we divide GT by 1 minus beta. And then we make this update. So similar to SCD, but this time the gradient is Vt, the accumulated velocity, or the accumulation of GT, divided by the square root for accumulation of GT squared, the magnitude. And we add the small number just to avoid dividing things by a number close to 0. So in the beginning part, this can often happen. So therefore, we need to be careful about the warm up. I think there's also a item W, which maybe take care of this issue. And so the point is that here you see we actually update this theta t not by GT, but by a accumulation of recent GT, so that we figure out the correct direction, a good direction is in this direction. And we don't waste much time moving, fluctuating, or oscillating in this direction. So this Vt is accumulation of recent GT. And the big GT is accumulation of GT squared, the magnitude. As I mentioned here, you see the magnitude is so small along this direction. So if you divide eta t by the square root of the magnitude, you're actually making this update bigger, right? So you use a bigger learning rate. So that's the idea. Just to convince you that indeed this type of formula, they are actually accumulating this GT or GT squared. Let's just look at this one. So suppose we start from G0, big G0 equal to 0, and then G1 equal to beta G0, which is 0, and then plus 1 minus beta G1 squared, right? And the G2 will be what? Beta times this guy, beta times this guy. I just copied here, plus 1 minus beta G2 squared. And then you move 1 minus beta out. So it will be beta G1 squared plus G2 squared. And G3 is beta times this guy, beta 1 minus beta. I just copied here. Okay, I copy here to here, and then plus 1 minus beta G3 squared. So if you move 1 minus beta out, you get a beta squared. Okay, beta squared, right? G1 squared plus beta G2 squared plus G3 squared. And so now you see a pattern. So GT will be 1 minus beta, and then beta T minus 1, G1 squared plus beta T minus, this should be 2, T minus 2, G2 squared, and plus beta and GT minus 1 squared plus GT squared. So if you look at this sum, so clearly you are doing this weighted sum, right? Weighted sum for GT squared, but you gave more weights for the more recent GT. For the remote GT, for example, G1 squared, G2 squared. So this beta, remember beta is a number like 0.9. So if you keep raising this power, so this quickly becomes 0, right? So therefore, you are actually only accumulating the GT squared for the more recent T. So it's a weighted summation of recent GT squared. And here you also see why you want to divide this by 1 minus beta, because when you divide GT by 1 minus beta, you get a accumulation, the real accumulation, right? So therefore, as I mentioned before, so here we are actually using this formula. We use this formula to accumulate the recent GT, and here we use this formula to accumulate recent GT squared. Again, we do this element-wise, and then we divide this by 1 minus beta or 1 minus gamma to get this real accumulation. And then we update according to accumulated GT, but we also divide this by the magnitude so that those elements, those parameters with small derivatives, with small derivative of a small magnitude will be updated more because we divide eta t, which is scalar learning rate, by the square root of the accumulated GT squared. This is also relevant in this ReLU, the so-called sparse feature. So if most of the time, for example, for a particular h, which is computed by ReLU, if most of the time a particular component or neuron always get 0, then this neuron will never pass the gradient, right? And only in the rare case when it is equals 1, it passes the gradient so that those parameters start to learn. So that's the idea. That is the sparse feature. So when it has a chance to learn, rather you want this to learn quickly. So that's why you want to like adaptively adjust the learning rate by the magnitude, okay, to deal with the sparse feature. But even in this example, you see that if this gradient is too, suppose it's a good direction, it's directly go this direction, right? But in this type of situation, the gradient along this direction is just too small. So you want to make it bigger in the learning, in the updating. Okay, so this is a Adam optimizer, which is very commonly used in machine learning. So nowadays, I think people stop doing research on this optimization because people seem to be happy enough with Adam optimizer. Okay, so that's the optimization part, which is the practical implementation for stochastic gradient descent. So Adam actually combined two existing ideas. One is a momentum. So SGD with momentum. We use this to accumulate momentum. Another is called AdGrad, adaptive gradient, or later this so-called root mean square prop. So that is the root we actually accumulate GT squared and then take square root. So it combines the strengths for stochastic gradient descent with momentum and this so-called RMS prop, root mean square prop, or AdGrad, and to get this algorithm, which now is very commonly used in training the neural network. Okay, so I think that's probably it for this lecture. We can stop here.